Hello everyone. Today I am going to discuss a problem from proakis textbook, which says that a finite duration sequence of length L can be represented as x of n equal to 1 in this range and 0 otherwise. We have to calculate endpoint DFT for this sequence for n greater than or equal to L. First, let us see for n equal to L. If n equal to L, then we have a total of L samples and each is of magnitude 1. We don't find any zeros here. Let us take L equal to 6, then n is also 6. Then from 0 to 5 we have a magnitude of 1 for every sample and we don't find any 0 here. Now to calculate DFT for this sequence, we can use this formula. This formula can be represented using a matrix. It is given by coefficient matrix times x of n. Here x of n is a vector with value 1 from index 0 to L minus 1, and this is quotient matrix. Here Wn is nth root of unity. If we multiply this quotient matrix and x of n, we will get L as our first entry and remaining all entries as 0. We will get remaining entries as 0 because all the values of x of n are 1. If we multiply second row of coefficient matrix and with all ones, then we will get summation of these terms 1 plus wn square so on wn power n minus 1. This is 0 because sum of equally weighted n roots of unity gives 0. Same for all these. So we have L for k equal to 0 and 0 for other values of k. We can see here there is a peak at k equal to 0 and it is 0 for every other value. We have a relation omega equal to 2 pi times k by L. Here k is equal to 0, which implies omega is also 0. This implies that there is only 0 frequency component in the interval 0 to L minus 1. Here x of n is aperiodic. Its transform is also periodic with a period of 2 pi. So from 0 to 2 pi, we have frequency at 0, and from 2 pi to 4 pi, we have frequency at 2 pi, and next we have at 4 pi, and so on. As the information from 0 to 2 pi is same as that of 2 pi to 4 pi, it is sufficient to take only from 0 to 2 pi. Other information is redundant. So we have only 0 frequency in the interval 0 to L minus 1. We can also reason this intuitively. We can see that this is the expression we end up in one of our step while deriving DFT from DTFT. Here we are calculating DFT for xp of n instead of x of n. We started with x of n, but we are calculating DFT for xp of n. Here xp of n is the periodic repetition of x of n with period n. Here for n equal to L, we don't have any zeros, we have all ones. So periodic repetition of this x of n is a DC signal. So its frequency is zero. So you can reason this way also. Like we have only zero frequency component in our sequence. Now for n greater than L, let us take L equal to 10 and n equal to 50. X of n can be taken as a vector with values 1 from 0 to 9 and it is paired with zeros at remaining positions, and it is the same formula. If we multiply this quotient matrix and this x of n, we will be ending with this expression in every row. By calculating for n equal to 50 and n equal to 100, we will arrive at these spectrums. And if we calculate x of omega from DTFT expression, we will get x of omega as this spectrum, magnitude of x of omega. We can see that 50 point DFT and 100 point DFT gives the same information, except that 100 point DFT is more denser than 50 point DFT. So it is more easier and more finer to track x of omega from 100 point DFT than 50 point DFT. We can see that for spectrum of n equal to 100 is more closer to magnitude of x of omega than transform of transform for n equal to 50. The only difference we have in n equal to 50 and n equal to 100 is we have paired with 50 extra zeros. This indicates the importance of padding with zeros. By padding with zeros, we can get more finer structure of our spectrum, which is more closer to our magnitude of x of omega. So this indicates the importance of zero padding. Thank you.